we have today, or the virtual roadshow, which is sponsored by AACOMA project, which is a European funded program to boost the industry and the technological applications of composite materials in the region of Western Belgium, Walloon-Liège region and Limburg, Southern Holland or Netherlands, also the region of Limburg, and the region around Maastricht and Aachen in Germany. So the concept of this AACOMA project is that a lot of different parties with different fields of expertise have joined forces to bring new technologies, demonstrate the latest technologies, educate the market on the usage of composite materials. In view of this setup, we have organized a digital event to showcase you the expertise and some of the know-how available in the region on composite materials. Today's presentation of Didier, I will introduce in a second, is part of a three-day program where different speakers have talked about production methodologies, the market of composites, the impact of COVID crisis on composites. We also had an online matchmaking event on this 3-day agenda. And all these recordings will, of course, be sent of you after the meeting today. You will get a recording as well, but also they will all get bundled on the AACOMA website, which will be launched soon. So also in the future, if you need any kind of information about composite materials, the applications, or maybe find via networking a kind of a company in the region working on the same technology, the AACOMA website is something to look up in the near future. Today, we have the last speaker of the 3-day event, which is engineer Didier Garray. He has more than 30 years of experience in engineering and working at Sirris, a scientific institute in Belgium, and he's specialized in composites. Didier will today give a longer presentation all about the basics of composites. So we will have a broader presentation about the materials, the specifications, the process parameters involved. He will give some guidelines on the designs and how to design a composite product. And then he will close his presentation with a tour of the killer applications of composites we have around. Final word from my side, just an organizational point of view. Please mute your mic during the presentation of Didier so he can present nicely. If you have a question, feel free to put it in the chat, and we will come back to your questions at the end of the meeting or of the presentation. We have a time slot to answer your questions and to learn more from the experience of Didier on this field. Good. With this said, I would like to give the word to Didier to give his introduction and his presentation on the basics of composites.
Thank you, Manuel. First of all, do you hear me, everyone?
Yes, I can hear you.
Okay, perfect, thank you. Now I will share my screen. So I hope it will be okay for you. Do you see the presentation? I do not see you anymore, so if you could give me a feedback by...
I don't see your presentation at the moment.
You don't see my presentation? Oh. And now?
Yes, it's working.
Okay, so this is... And now?
Excellent.
Okay, perfect. Okay, good morning, everyone. Like Manuel explained, thank you for the introduction, Manuel. I will present you the wonderful world of the composite materials, but the basics. For sure, we will not go into depth into all the different capabilities of those materials, but I hope you will be, after this presentation, convinced that this material, composite, and I have to say these materials because there are a lot of them, are very interesting and could be very useful for your applications, whatever they could be. So this presentation will be divided into different sections. The first one will be a kind of definition of what is a composite material, with some introduction of the different components, the materials that are used independently, the role of the different components. The characteristic is also a part of this presentation, and like Manuel said, I will also have a part dedicated to the market and the application, so you will see that it's very, very broad in terms of capabilities of this material. So let's start with first the definition. What is a composite material? So in fact, composite material, this is a combination of two main components, the fibers for the reinforcement and the matrix. But I have to introduce directly one, not a limitation, but one specification. This is the distinction between what we call filled or reinforced polymer against a composite. In fact, when you add some additives into a polymer, you can have extended performances like UV protection, thermal or electrical conductivity improvement, flame retardancy. You can add different things into a polymer. We are there speaking about a filled material and not a composite or a reinforced one. If we are speaking about a reinforced material or composite, we are mainly thinking about the introduction of fiber. But not only, you could also have some beds, talcum, that gives material mechanical improvements. When we are talking about fibers, we can also have the distinction between short, long, or continuous fiber. And only, in my point of view, only when we are thinking about continuous fiber, we can talk about composite. For the rest, for sure, you will have improvement in the performance, but this is not really what a composite could propose. What is important to know is that this reinforcement will mainly give strength improvement and stiffness improvement, but main strain, but will also bring a lot of anisotropy into your product. So when we are speaking about additive dispersed into a matrix, we will talk about matrix improvement, and we can get a kind of anisotropy. When we are speaking about composite, we are speaking about organization of fibers where a matrix brings cohesion, stress distribution, and protection against the environment of this or those fibers. And for sure, there are so many capabilities that the boundary between both definitions is very, very fuzzy and not obvious in all cases. But what you have to take in mind is the fact that when you add additive, you change the properties of the polymer. When you are thinking about composite, the fiber is the main product and the matrix brings the coherence between them. We talk about matrix and fibers, so we are not going in detail into what is the fiber, what are the different kinds of fibers. You have for sure what you know, probably, the glass fiber. This represents a lot of the composite market. A lot of means that nearly 90–95% of the composite market is driven by the glass fiber industry. Why? Because it's a low-cost fiber with high mechanical performance, with some insulation in terms of thermal or electrical performance. That's why the glass fiber is the main used reinforcement for what we call composite. But you also know about carbon fibers. There, for sure, we are talking about high-performance structural composite. The difference between the previous one is that we are here thermally and electrically conductive through the fibers. We also have to mention the fact that the carbon fiber have very poor performance in terms of flexibility. So you cannot make a knot, for example, with this kind of fiber, or the very sharp angle are not easy to manage with this kind of fiber compared to the other one. As a kind of fiber are the aramid fiber, and the commercial name is probably well known than the aramid 20 name. These are the Kevlar or the Twaron. Kevlar or Twaron, or the more generically talking, the aramid fiber, are dedicated to high damping and impact performances. Those fibers are also have also very high specific strain. They are also used to have a very high cutting protection for the application, for the use of the operator, for example, like the next one, which is called the ultra high molecular weight polyethylene. And here too, the trend name or the commercial name is better known. This is the Dyneema or the Spectra product. Once again, this fiber is dedicated to very high impact performance till the ballistic protection. It's also used for application where a low friction coefficient is asked. And one of the drawbacks of this fiber that we have to mention is that there is a limited use temperature, let's say around 120 degrees. For the higher temperature, you will have a very large decrease of the performances. Less known or more confidential fiber, if we can call it, there are the basalt fiber. Those fibers that are emerging now for 10-15 years are dedicated to high temperature composite. We can reach with those fibers much more than, for example, 500 or 600 degrees. For sure, the matrix also need to withstand those fibers. But if it's possible, those fibers are quite low cost compared to the carbon fiber, and with similar fiber or even a little bit higher in terms of specific value than the glass fiber. And yes, metallic fiber can also be used for composite production, fabrication or design, where we are talking about very specific application and expected properties like electromagnetic shielding, electrostatic discharge, and even to give more density to the product, the final product. The advantage then is you can use the composite production facilities to make very complex shape, and the high density of the fiber, the steel or the metallic fiber, bring the inertia. And last but not least, the natural fibers. Natural fibers like flax, hemp, jute, cotton are fibers that are bio-based. So this is really the best option when we are talking about circular economy. And even if some, it's not obvious, some fibers, some natural fiber can bring very, very interesting mechanical performances. And for example, the flax fiber presents similar performance than the glass fiber. And we will see that later in a kind of table for the summary of the properties. But first, we have also to take into consideration some pros and cons of those natural fiber. The pro, I said already that, low cost. It's neutral for the carbon footprint, and for sure it's a renewable material. But if you are now talking about more industrial processing interest, we can say that this is a fiber which is not abrasive for the tooling. Compared to the glass fiber, this is a large advantage. We can also talk about good specific properties, strength and stiffness, but also in terms of damping or acoustic insulation, thermal or acoustic insulation. Now, the cons. Yeah, for sure, this is a natural fiber, this is a natural product. There is a risk of water absorption which also leads to reduction or modification of the mechanical properties. Low thermal resistance. So in fact, this is quite limited in some cases, and you will see that later. But if we are at the range of 230 degrees, you have a very drastic risk of reduction of the mechanical performances. And last but not least, there is a quality dependence on the geographic growth area and the year-by-year meteo. In fact, you must, because this is a natural product, you must consider it as a living product, and like the wine, for example. And wine is an exact, perfect comparison to those fibers, because depending on the region or depending on the year, you could have good or bad product. This is very similar. I already introduced this table of comparison of the fiber performances against the concurrency, which is the metal product. You see here the natural fibers that are presented in the second part of the table compared to the more conventional fiber, the glass, carbon, and aramid. And like I said, the competitors to see if there is an interest or not of using composite is the metal material like steel, aluminium, or titanium. You see also there are several columns with properties that are very interesting when you are designing a product. The first one, Young modulus, is dedicated to the stiffness of the material. And you have here the comparison between the raw value for each material in terms of fiber, for sure, for the first one, and in terms of isotropic performances for the metal. And the second interesting column is about the tensile strength. So it's written, it's the strength characteristic. You can see that, for example, the value for the glass, carbon, and aramid are in the range of the metal performances what concern the stiffness, Young modulus. When you are looking now about the strength, you already see here on those value that we are talking about an increase, an improvement of a factor of 2, 3, 4, 5 compared from the metal competitor for the fibers. But in fact, we will not compare the raw material together, the raw properties, sorry, of those materials together. What we are commonly using is the specific value. Specific value means that you take the raw value divided by the density, and so you are able to compare the different material more homogeneously. And you see here that you see that the fibers, glass fiber, are nearly at the same range of all the competitors in metal can propose for the stiffness. Carbon proposed already a factor of 4 to 5 compared to the competitors. We are speaking here about the stiffness. If we are now looking about the natural fiber, you can see that some of them are not really of good interest, but flax, as already mentioned, for sure the best product available can propose performances in terms of stiffness that are very interesting compared to the metal. But in fact, we are here, like I said, in a range of a factor of 2 to 5. If we are not now making the same comparison, but in terms of strength, we see that the order of magnitude or the order of improvement is not a factor of 2, 3, 4, 5, but a factor of 10. We are here at the range of 200 more or less for the metal, and we can reach easily with the fibers, even for the flax fiber, a value above 1000, even 2000 or more. So we can here say that we are a one order of magnitude. This is coherent with what I said. When we are talking about composite, this is more with the aim of putting in advance the strength, and in second advantage the stiffness. You have to take that into account. So I said at the beginning that the composite material is a mix between fiber and matrices. And the matrices, we also have different kind of them. The first distinction is about the nature of the matrix. We are here at the end of the slide, MMC, CMC, and CC. These are what we could say not organic matrices, metal matrix composite, ceramic matrix composite, carbon-carbon. These are products that are dedicated to very, very high and confidential applications. The more common products are the organic resin, like thermoset or thermoplastic. I will now try to explain you what is the difference between thermoset resin and a thermoplastic resin, because this is very, very important. The most known resin, thermoset resin, are polyester and epoxy, but you see here that there are a lot of other possibilities: phenolic, vinyl ester, cyanate. All of them are processed like liquid resin, very low viscosity material, meaning that you can use this flow capability to wet a dry architecture of reinforcement. Those liquid resin are processed by a curing polymerization cycle. We are here talking about chemical modification of the product. Chemical modification means that you have very low and even no recycling capability or very hard way to obtain that. To be sure that everyone understands this product, I have as a comparison and as illustration another example that is more from the common life. This is the concrete. Concrete is in fact also a combination of different materials that are, when they are separated, you can take them a few time in terms of weeks, months, independent. But when you mix them together, the sand, the cement, and the water, and even some stone, if you want to bring some mechanical improvement, you have a final product that is chemically modified and similar to this curing or polymerization. And at the end, like for the thermoset composite, you have very, very high difficulty for the recycling of this product. We are really at the same range of the material. Now we are presenting the thermoplastic resin. For sure, there are some names for the product, like polypropylene, polyamine, PP, PA, PE, PPS, PEEK, that are more or less well-known product or range of material. Here we are speaking about a high viscosity material. So we are not at the level of the liquid like for the thermoset, we are more at the level of, let's say, pasta, honey, something like this. The process is also totally different. We are speaking about a reversible process cycle. This is a physical process. We use the thermic of the product to bring it into a fluid, or let's say past a high viscosity fluid stage, and then we can give him the shape, and by cooling it, you get the product at the right geometry or the right shape. Like for the previous example, I have an illustration that you probably better know. This is the chocolate character that you can find in the shops during Christmas or Easter. This is exactly the same system. The chocolate is in a solid state till you reach a typical temperature where it becomes fluid. You put it into a mold, you make some rotation to avoid to have a compact and fully filled product. And then when you reduce the temperature, you have a solidification of the chocolate, which gives the final character. Interesting information about that. The thermoplastic resin are also very good for impact performance, especially compared to the thermoset. I hope that you very well understand the difference between the two kind of organic matrices, because this is important for, I would say, the good understanding of the rest of this presentation for basics for composites. Now I'm going on to the drawback of the thermoset composite, because it was, let's say now 20 to 30 years ago, a great challenge in terms of ecology in the world of the composite material and activities. There are great problems, issue due to what is written here, the solvent release, mainly the styrene. Also, for the economical point of view, this is a long time processing. Chemical modification could, which is called curing, could ask some hours to be fully finalized. And like I already said, there is a very high problem concerning the recycling of this material. So, like I said, it was the problem 20 to 30 years ago. So some solutions were proposed, and for sure the provider or the supplier of the thermoset resin worked onto this problematic to solve it, and they proposed resin with low solvent content or solvent release capabilities. Also, the processing technology have been improved by closing mold instead of open system. So a better control of what was released and a better handling of those solvents have been treated by the process. And what was also very important, development of alternative composite. So you have in the previous slide the presentation of the difference between thermoset and thermoplastic, but that was just the matrix. If you want to combine them with the fiber, you will see that it's not as obvious, due, for example, to the high viscosity of the thermoplastic product. But some solution exists, and this is the emerging of the thermoplastic composite. Thermoplastic composite can be proposed in different way, but there is also another system that has been developed. This is the low viscosity thermoplastic, which allow to keep the same process as the thermoset processing technology allows. And the cyclics and helium from AACOMA are very well-known product and a very well-known solution for this way of working. Both of them, thermoplastic composite or this low viscosity thermoplastic, present as advantage short time processing cycle, better impact strength, this is important, welding possibilities. That's meaning that for joining those kind of material, you have a new kind of technology available, which is the welding. Welding is working on the temperature and also the fusion of the interlayer instead of the full material. But this is a real important advantage compared to the thermoset material, where, let's say, only gluing or mechanical fastening can be proposed. And for sure, the easier recycling capability. When we are talking of this example of cyclic product, we can see that when we want to process it by chemical reaction, we reduce it to monomer or oligomer, very, very short length molecular system that are very fluid. The viscosity of this CBT chain could reach more or less 1/5000th of the value of the PBT, which is the linear recombination of those molecules. So by this way, it's possible to flow the product, the matrix, into the dry reinforcement network. And we can adapt the reaction time by playing onto the chemical data of those material, and also with the temperature. Newer is the helium product. This is a matrix produced by AACOMA. And once again, the advantage of this specific product is dedicated to what I already mentioned, the circular economy, the capability of using production technology of conventional thermoset techniques, even for large parts like the wind turbines. And the capability of recycling is, of course, a very high advantage of this. And they also propose different ways of mechanical or reactive recycling. I mentioned the fact that thermoplastic composites have been also developed with as objective to avoid the need of flowing the resin into the reinforced network. How can we do that? We can do that by placing the matrix already at the right place in the raw material. And we can do that by different ways. The first one is the comminglet fibers. So you can see here the presentation of a bundle of different fibers, blue and yellow. You can imagine easily that, for example, the blue or the dark one are the reinforced fiber, that could be carbon, glass, or even what we already present, and the yellow one are the matrice fiber. Because if you can process a matrix, a thermoplastic matrix, in terms of bulk material, you can also, in sometimes, not all, but a major part of them, can be processed in fibers. So we can use fibers to bring the matrix at the right place in the raw material. So no movement apart from fiber to fiber, but in the cross section, you do not have to have a very high flow capability. So this is the first way, comminglet fiber. The second way is the coating of the reinforced fiber by the matrice. So here too, you have the right material at the right place with a minimum of movement of the matrice. And the last one, this is the lamination. You can already realize some plates where the reinforcement and the matrix is already present at the right place, at the right concentration, the right content. And this is what is commonly called organ sheets. And then you get here a compact and solid structure plate that you have to manage. For the two other one, you can have a flexible fabric that need to be treated physically by thermal action, heating and cooling, to get the final product. But here on the left side, you have a flexible product, a flexible raw material product. On the right side, this is a plate, a solid, stiff structure. I mentioned the difference between thermoset and thermoplastic, but if you are now looking on what is available in terms of different grade or different kind of material for the thermoplastic, you see that there are a lot of, with different capabilities, from the commodity plastic till the high performance engineering plastic, and with different possibility. How to choose that, how to select what you want. In fact, you are, because it's available, you are able to choose this kind of material for the final composite, thermoplastic composite product, depending of the operating temperature, for example, mechanical performance. Yeah, in fact, I put that into brackets because, as you know, this is not the matrix that will give the performance, the mechanical performance of the composite. This will be the fiber. So, of course, it could be interesting to have stiffer or high performance matrix, but in fact, this is the fiber that gives the real performance of the composite. But the chemical resistance, here the fiber will not see the fluid or the material that is in contact with the product. This is the matrix that is in contact, not the fiber. So the choice of the matrix is very important for this parameter. And for sure, you have also to take into account the economical point of view, and the cost of the product is also partially and even highly driven by the matrix nature. Just here to explain and to show that commercial product already exists with different combination of those material. For the reinforcement, you can have carbon fiber, pararamid fiber, and flax fiber for this supplier, Chef Techniques in France. But even with all those combination of fiber, you can see that you can even choose or select the matrix you want to work with. Polyamide, PBT, PPS, till PEEK. And you already see through the figure that different other parameter could be asked to the supplier. This is the architecture. And we are now going into a new parameter dedicated to the composite material. This is the architecture of the reinforcement. You probably know quite good the different architecture that are presented here and that are circled here. These are the cutted fibers, the UD web, or the fabric, the twill weave. So here the fiber are cut. So if I come back to my definition, we are more in a reinforced product than in a real composite. But okay, like I said, also this is quite fuzzy to clearly distinguish both material. So here it's a way of having the reinforcement, cut fibers, randomly dispersed. Or you have the UD web. All the fiber are oriented in the same way, and the weave, twill weave or other kind of weave or fabric, you have here a part of the fiber that are in one direction and a part of the fiber that are in the perpendicular direction. We can talk about equilibrium weave if we have, for example, 50% of the fiber in one direction and 50% in the perpendicular direction. But you can see also that if you know those architecture, there are a lot of other capabilities giving different and specific properties. Triaxial weaving, multi-axial weaving. So the fiber are in the three direction oriented in a controlled way. There are also the braiding. Braiding is probably not well illustrated onto the table, but well onto this figure. You can see how a braided structure can be realized. And you see clearly that this is more dedicated to hollow structures. And the last line is dedicated to multi-layer 3D structure. And we are here in the world of the sandwich structure. Sandwich structure are very well specific product dedicated to bending capabilities because the material is placed at the upper and lower side of the thickness of the part to give the best stiffness for the product. This is already a design application. Now, concerning composite, when we discussed a little bit earlier about the performance of the fiber used for the composite compared to the metal or to the competitors, I mentioned the fact that we were with the performances of the fibers, not performances of the composite. Now we are going one step further with the performance of the composite, taking into account the parameter architecture. And here, to understand it, you see that, for example, we take a carbon fiber with very high performance in one direction, the horizontal one. And we want to compare it with the isotropic material, the metal. And you see that, of course, the fiber propose better performance, even 2 or 3 times or even more than the metal, but only in one direction, while the metal proposes in the same performance in all directions. So if we want to suppress this drawbacks for the fiber in the perpendicular direction, we have seen that we can propose a product which is a fabric or a weave structure with fibers in direction 0 and fiber in direction 90 degrees. But for sure, if we make this with only 50% fiber in the horizontal direction, you also have a decrease of the performance by 50% due to the reduction of the number of fibers into the product. But you have no performance in the perpendicular direction. This is not sufficient to have a fully isotropic material. You have to use several layers with, for example, 0.90 and the next layer with 45 minus 45 to have a quasi-isotropic product. In fact, we are more talking about 0, 60 and 120 degrees to have a quasi-isotropic product with composite material. Now that you have well understood the difference between fiber performance and the influence of the parameter, the architectural parameter, we can have a look onto this graph, which presents comparison, generic comparison about what can propose a carbon fiber composite in blue or a glass fiber composite compared to the competitors, the metals. First thing is to look about the axis. On the horizontal axis, you have the specific stiffness. You know what is now a specific stiffness. This is the stiffness, the raw value divided by the density. And in the vertical, you have the specific strength. First thing is that you can see through the scale that you have a factor of 3 between the metal and the best product in carbon fiber in stiffness, while you have the factor of 10 already mentioned for the strength. This is once again mentioned onto this graph. I will now go a little bit more in detail into what is CFRP UD T800 with a Phi factor of 60%. Oh, what? That means that carbon fiber, reinforced plastic, UD reinforcement, you know what is UD. T100 meaning that you use a very high performance grade of carbon fiber, and the Phi factor is the fiber volume fraction into the composite. That means that you use a process that is able to put 60% of fiber into the full volume of the product. This is a high capability technology or process. And with this, you can have a very, very high improvement compared to the conventional metal. But in fact, you have a UD material. So if you want to realize shroud, for example, for a bridge, no problem, that's the perfect product. But now, if you want to use it for a more common and more universal performance product, you have to take into account the different parameters. T100, if you come to a more conventional fiber, which is the T300, in fact of T800, sorry, you'll see that you have a decrease of the performance. If you are not talking about quasi-isotropy in terms of UD direction, this point comes here with all the other parameters that remain the same. So that means that you are now closer to the metal, but still with a kind of interesting improvement. If you use T300 fiber, you come from this point to this one. And now, if you do not use a specific high-performance process, which allows 60% of fiber into your product, but only 30, you are here. And you see that you become to be less performant in terms of stiffness, and you are still with carbon fiber, but you remain very interesting in strength. So now you understand why it's very, very interesting and very, very complex to design a composite product that is better than a metallic structure, even if you use all the best product. The carbon fiber, the T100 or the T300 or the T800 are very well performant structure, but you have to take into account all the parameters to be sure that you design your product with the same performance or better performance than the metallic. If you are now coming from the carbon area till the glass fiber area, you see with the same parameters that high performance process UD bring you interest. If you are not talking about quasi-isotropic glass fiber, you are lower in stiffness and the same range of for the strength. Sorry. But that does not mean that none of those products are interesting. For sure, composite can bring information about mechanical performance, but not only. In fact, what we know now is that composite bring specific strength and stiffness, mainly strength. But also you can play with other parameters like the chemical resistance by choosing the right matrix. Good fatigue behavior also. This is something I did not mention earlier, but it is important. And what is really important to know and to understand is that composite material is not something that you can find on the shelf and you can use it like you do that for aluminum or metal just by tooling it. This is a product. This is a material that is built during the building of the product. So both are built together. That means that you have all the capability of parameter to design your material and product together to be with the best set of result compared to the requirement. You want electrical insulation or conduction, you take glass or carbon fiber. Idem for the thermal properties. You want damping performances, you can use aramid or Dyneema or Spectra fabrics, sorry. You can also play with the natural fiber for the lowest damping properties that are needed. You want process a very large part, no problem. Of course, you need to have a more dedicated to that, but the material is able to be processed in complex shape when you are talking about large part. You want to weld it, okay, use thermoplastic instead of thermoset. You are concerned by the cost. You are also able to play with the choice of the material. If you are more interested by a low-cost material, you will probably use a commonly commodity plastic for the matrix and a glass fiber. If you are not very oriented to the performance of the material, then you can go till PEEK and carbon fiber. So you have all in hand to design what you want in terms of your specifications. I said that composite products or composite material are mainly defined by two components, the matrix and the fibers, but in fact, even the matrix could be additive, filled, and some of them could have interesting advantages. For example, we can add nanotubes into the matrix to bring the matrix more electrically conductive or thermically resistant. Or even here, this is a specific application. If you put nanotubes into a matrix, or material, polymer material, organic material, you can have anti-fouling or biofouling performances. That means that the shell of the boat, for example, are prevented for the anchorage of the shells from the sea, and then you will not get a drag reduction, a drag performance reduction of the boat by all of those impurity or pollution onto the shell, which can cause large cost increase by this reduction of the drag performance. Also, if you want to add some traceability into your product, you can add particle like the chromition into your product, and they will be acting or reacting with light, and you can see this is if this is or not an original material, because for sure the competitor or the counterfactor will not use the same capabilities. So this is an opportunity not always used, but that could be very interesting if you are talking about anti-counterfeit. Now, I'm going to present you some applications. Oh, I see that it's already 10 to noon, so I will go fast. The first one is the use of the composite with electrical insulation in the electronics or in the medical parts. If we want to talk about a possibility of using large structure of freedom of shapes, we can also have this opportunity given by the composite. And here I will go directly to the idea is the fact that we can use, what I wanted to do for sure. Yeah. The idea is that sorry. Yeah, okay. So the idea is that the tree is in fact the composite part and is dedicated to the cover-up, the camouflage of an antenna, RF antenna, just to show that there is a possibility of using composite in different kind of applications. For sure, for laser, you can also have a very nice illustration of the composite capability, freedom of shape, large part of production. For the corrosive resistance, the chemical protection, you also have application in offshore components or in storage of transfer of chemical fluids. And this can be used or in the new products or in the recovering of tubing, for example. So this is not just dedicated to new products. You can also apply composite as recovered solution. Recovered solution not only for the corrosive and the chemical application, but also for some bridges. You know that some bridges are very impacted by the salt or by the rain that can corrode the steel reinforcement that are present. So reinforcement recovering of those building structure can be done by composites. For sure, use in application where the lightweight is asked, like aviation, aeronautics, this is very important, and you can find composite not only in the furniture inside of the plane here, but also on the frame structure, and more frame components are now in composite because they are certified in terms of strength, capability, reproducibility, and so quality control. It's enough to be used in those applications. For train application, the same. When you want to realize a record, weight saving is important. So you use composite instead of using the conventional material that are used for the common use of this, for example, train. For a trailer, this is a little bit different. The interest of having a light structure is not for better performance in terms of speed or something like that. In fact, this is due to the legislation, the rules, because you are allowed to put, in Belgium, 40 tons on the road. So if your truck is lightweight, you can bring more payload. And this is the interest of using composite in this way. Compared to steel, for example, you have 5 tons payload more available onto your transportation. For the automotive industry, for example, another advantage is that you can combine different components into one structure due to the complexity available of the process and the material. So here, for example, 28 parts of steel or metal part have been reproduced into only one structure in composite material. And for sure, combination of different material is still available. This is what we call hybrid materials. And for example, here you see example of overmolded structure with thermoplastic overmolded with short or no fiber onto a composite thermoplastic, and you can even imagine that you have still metallic insert into the product, like here. For the boat industry, this is also really important to have the lightweight and the large capability in complexity in shape. For the wind turbine, the interest of having very large wind turbine is the fact that the surface concerned by the wind turbine is directly linked to the dimension of the blade, for example. So coming from 12-meter blade till a 100-meter blade, you see that you have a lot of energy concerned by the proportional to the dimension of the product. And you can see here one of the blades, which is more than 80 meters long, transport from the production seat to the exploitation seat here in Danish operations. If you want to use it for bridges, for example, you can have different advantages. Or this is during the building, the handling and the installation, you can use very low weight capabilities for building the bridge, the structure, or during the service you can also take the advantage of the weight saving, for example, for mobile bridges, where the motor or the engine which is driven this bridge is also really proportional to the weight you have to move. Here it's an example of a structure that is dedicated to the broadcast activity. And the target, the specification, were to limit the number of operators. Only one operator can manipulate an arm with a camera on the end, with a capability of 12-meter long structure. And for sure, the stiffness is here important, because if you do not have this kind of stiffness, you will have vibration at the end of the arm, and so you will have also some waving of the image that can give some seasick to the audience, which is not required for sure. When you are talking about speed or very high inertia, you can see that even in the industrial sector, like the weaving, the textile industry, you have the use of the composite, which is important. Here, for example, this kind of frame can reach a speed or alternate speed of 5,000 cycles per minute. So you imagine that weight saving can, with strength, can bring very large advantage to the structure. For sure, sport applications are also very well using composite material from the car industry, Formula One, the bicycle. You can see here in the fishing rods the interest of having a material which is strength when keeping very light opportunity. So you see that there are very large, broad application dedicated in the sport for the composite material. Medical sector can also be very interested by composite material. Here, for example, the advantage is really dedicated to the customization capability and the lightweight of the product, the prothesis or the orthesis. So there is also here a large capability, a large activity in terms of composite use. And not the last one, but nearly, I like this slide because it proposes something which is absolutely not dedicated to mechanical performance, but just to the look, carbon look. The interest for design and fashion of the composite material is absolutely dedicated to the aesthetism, the look, and not the performance, except one. And this is the only question I ask to the audience. Do you know which product on this slide is using the mechanical performance of the composite? I hope there is someone.
Sure.
the shoe. Yeah, I do not know who, but you will probably get a gift at the end. Manuel, you manage that? Okay, that's for sure. This is the shoe, because you can see here the heel is really oriented design and fashion and specific to the capability of the composite. And for sure here the mechanical performance is of first importance. And last, no, for sure, the natural fibers are also used in a lot of different applications, furniture, different as a way, and specific to show the performance and the good damping properties. You have here an helmet which has been produced in flax fiber. They use it in a racket, tennis racket. And here for the sound absorption, it was being used also to put a surrounding structure that prevent from the sound the door of a car. So I hope that through this presentation, I give you some indication, and know you are better able to see what is possible with this material, this amazing and wonderful material, which is the composite. And when I see the material, I have to say those materials, because as you know now, there are a lot of capabilities and possibilities and variabilities into the production and the parameters to use and to process this material. Thank you for your attention.